Alright, let's go. Number 12. 30 years of nothing. In the late 1980s, physicists were not hunting for dark matter directly. They were refining detector technology built for something else entirely, searching for proton decay, testing whether matter itself was fundamentally unstable. The byproduct of that engineering became the blueprint for a different hunt. Standard cosmology predicted a WIMP, a weakly interacting massive particle, sitting just outside the reach of the Standard Model. Heavy enough to explain galactic rotation, weak enough to slip past ordinary detection. Build the shielding deep enough, the theory said, and eventually one would strike a nucleus and leave a signature. Detectors dropped a mile underground. Xenon tanks grew from kilograms to tons, and the signal never came. Xenon and ELS, the two most sensitive detectors ever built, pushed the WIMP nucleon cross-section limit down by roughly 9 orders of magnitude since the first serious searches in the 1990s. Every single run reports the same result, 0 confirmed detections. Physicists proposed the particle was lighter than assumed, that it interacted through a different force, that the detectors weren't yet sensitive enough. Each explanation bought another decade, another generation of hardware, and another null result. The most expensive nothing in the history of experimental physics is currently sitting a mile beneath South Dakota and Italy, and it has found exactly nothing. If the particle exists at all, it has now evaded a global, multi-billion-dollar search for longer than most of the physicists who built the first detector have been alive. What happens to a field when the leading hypothesis simply refuses to show up? The detectors kept listening, and what they eventually heard wasn't the WIMP at all. Number 11, the Neutrino Fog. Researchers building next-generation dark matter detectors in the 2010s were trying to solve a purely technical problem: how to shield a WIMP detector from every conceivable source of background noise, cosmic rays, radioactive decay in the tank walls, radon contamination. Standard detector design assumes that with enough shielding, the only signal reaching the core is the one you're hunting for. As sensitivity improved, a background no shielding could remove began appearing anyway. In 2014, Billard, Strigari, and Figueroa Feliciano modeled this limit in Physical Review D and gave it a name: the neutrino floor. Solar and atmospheric neutrinos, streaming through the Earth constantly, produce nuclear recoils that look almost identical to a WIMP collision. In 2022, the Xenon collaboration confirmed they were now detecting solar neutrinos directly inside a dark matter experiment, the first time this background had actually been observed rather than merely predicted. Engineers proposed directional detectors that could distinguish neutrino recoils by angle. Others proposed entirely new target materials. Both remain unproven at scale, and both add years and budgets the field may not have. This isn't a technology problem that better funding solves. It's a wall built into the physics of the universe itself, and if the dark matter particle sits below it, no detector we know how to build will ever see it strike. Not every candidate hides behind a wall. One was found by accident, chasing a completely different mystery. Number 10. Axions ADMX. In 1977, Roberto Pecci and Helen Quinn were not thinking about dark matter at all. They were trying to solve the strong CP problem, the baffling absence of a symmetry violation in the strong nuclear force that, on paper, should be there. Quantum chromodynamics allows for a term that would let the neutron carry a measurable electric dipole moment. Every precision experiment says that moment doesn't exist, constrained to a number smaller than 1 part in 10 billion. Pecci and Quinn proposed a new symmetry to explain the absence, and Steven Weinberg and Frank Wilczek showed in 1978 that breaking that symmetry would produce a new ultra-light particle. Wilczek named it after a dish detergent brand, the Axion, because it cleaned up the problem. Decades later, physicists realized the Axion's predicted mass and interaction strength placed it almost perfectly inside the dark matter window nobody had asked it to fill. The Axion Dark Matter Experiment, ADMX, at the University of Washington has spent over 2 decades tuning a microwave cavity through the candidate mass range. hunting for the faint photon an axion would produce inside a strong magnetic field. No detection yet, but unlike the WIMP search, ADMX has been closing off real specific mass ranges year by year rather than simply extending limits. A particle invented to fix an unrelated flaw in nuclear physics may turn out to be the thing holding galaxies together. If it is, we found the answer to one of cosmology's oldest questions by trying to explain something that had nothing to do with cosmology at all. Not every anomaly gets explained away. Some get walked back entirely. Number 9. The 3.5 key line. Astronomers studying X-ray emissions from galaxy clusters in the early 2010s were cataloging known atomic transitions, building precise maps of hot intercluster gas for entirely separate structural studies. Standard atomic physics predicts specific, well-documented emission lines from elements like sulfur and argon at known energies. In 2014, two independent groups, Esra Bulbul's team in the Astrophysical Journal and Alexei Boyarsky's team in Physical Review Letters, both reported an unexplained emission line at 3.5 kiloelectronvolts, present in stacked observations of dozens of galaxy clusters and the Andromeda Galaxy, matching no known atomic transition. The leading exotic explanation was a sterile neutrino decaying into an ordinary neutrino in a photon, a dark matter candidate hiding in plain sight in data that had already been collected for other purposes. The failure parade came fast. Later, deeper observations from the Hitomi satellite and other instruments failed to reproduce the line in some targets. Several groups argued it was an unmodeled potassium or chlorine transition, an instrumental artifact, or a statistical fluctuation dressed up as a discovery. The signal has never been fully confirmed, and it has never been fully killed. Somewhere in a decade of contested X-ray data sits either a decaying dark matter particle or the most persistent instrumental error in modern astrophysics. And after 10 years, no one has definitively said which. If dark matter isn't a particle decaying in the light, maybe it was never a particle at all. Maybe it's older than particles. Number 8. Primordial black holes. In 1966, Yakov Zeldovich and Igor Novikov were modeling the extreme density conditions of the very early universe, working through the mathematics of cosmic inflation and structure formation, not searching for dark matter candidates. Standard cosmology says black holes form from the gravitational collapse of dying stars, which requires billions of years of stellar evolution before the first one can exist. Zeldovich and Novikov showed that if density fluctuations in the first fraction of a second after the Big Bang were large enough in specific regions, black holes could have formed before a single star ever ignited. Stephen Hawking developed the idea further in 1971. These primordial black holes, ranging from asteroid mass to stellar mass, would be completely invisible, ancient, and gravitationally identical to any other dark matter candidate. In 2019, the Subaru Hypersuprime-Cam survey, led by Hiroko Nikura, used gravitational microlensing of stars in Andromeda to rule out primordial black holes as the dominant form of dark matter across most possible mass ranges. But a narrow window around asteroid mass remains stubbornly open. Every object in that surviving window is small enough to hold in your hand, dense enough to warp space-time, and could be drifting through the galaxy in numbers too vast to count. What if the dark side of the universe isn't made of anything new, just the leftover wreckage of a universe that started collapsing before it finished being born? For a while, an entire generation of physicists thought the mystery had already been solved. They were wrong, but it took a decade of data to prove it. Number 7. MACHOs, the theory that was killed. In the early 1990s, astronomers weren't inventing exotic particles. They were testing the simplest possible explanation first. What if dark matter was just ordinary matter we couldn't see? Standard assumptions held that dim, compact objects, brown dwarfs, neutron stars, old white dwarfs, collectively named MACHOs, massive compact halo objects, could account for the galaxy's missing mass if enough of them were scattered through the halo. The MACHO collaboration and the French Aeros survey began monitoring millions of stars in the Large Magellanic Cloud. watching for the brief brightening caused by a compact object drifting in front of a background star. Over roughly a decade of continuous observation, both surveys found far too few microlensing events to account for more than a small fraction of the galaxy's dark matter. Charles Alcock and the MACHO collaboration published their final results in the Astrophysical Journal in 2000. Closing the door. Astronomers proposed the objects were simply too small to detect, or clustered in regions the survey missed. Neither explanation survived the statistics. An entire leading theory built on the most conservative assumption in the field, that dark matter was just matter, was tested directly against observation and killed within 10 years. If the simplest answer failed this completely, what does that imply about how strange the correct one has to be? The next attempt didn't kill an idea. It broke a prediction that had held for 25 years. Number 6. Self-interacting dark matter. Cosmologists running the first large-scale structure simulations in the 1990s were trying to reproduce the shape of galaxies from first principles, starting from a universe of cold, collisionless dark matter particles that interact only through gravity. Standard cold dark matter simulations predict a sharp, dense spike, a cusp, of dark matter at the center of every galaxy, rising steeply toward the core. Actual rotation curves, measured across dozens of dwarf and low-surface brightness galaxies, kept showing something flatter, a broad, diffuse core instead of a spike. David Spergel and Paul Steinhardt formalized a possible fix in a 2000 paper in Physical Review Letters. What if dark matter particles collide with each other, not just with ordinary matter? A small amount of self-interaction would smooth the cusp into a core through collisional heating in the galactic center. Other groups proposed the discrepancy was simply a limitation of simulation resolution, or feedback from ordinary stars blowing gas out of the core and dragging dark matter with it. Neither fully explains the scale of flattening seen in the smallest, most dark matter-dominated galaxies. The core cusp problem is now over 25 years old, and the leading fix requires dark matter to have a physics of its own, forces, collisions, and entire internal life we've never detected. If dark matter can bump into itself, what else can it do that we've simply never built an experiment to see? If it can collide with itself, the next question is unavoidable. Does it have its own version of chemistry? Number 5. The dark sector. Particle physicists in the 1980s were exploring how hidden or hypothetical particles could couple weakly to the visible universe, largely as a theoretical exercise in extending the Standard Model. Bob Holdham formalized the mechanism in a 1986 paper describing how a hidden U-gauge boson, a dark photon, could kinetically mix with the ordinary photon through an almost imperceptibly small coupling. Standard cosmology treats the 27% of the universe classified as dark matter as a single particle species, the simplest assumption available. But the visible 5% of the universe isn't simple at all. It contains hundreds of particle species, 4 known forces, and an entire periodic table. If the dark sector mirrors that complexity even partially, it could contain its own forces, its own bound states, possibly its own version of atoms built from particles no detector on Earth is tuned to see. Physicists have proposed dark photons, dark Higgs bosons, and entire hidden sectors with independent thermal histories, but every experiment designed to find evidence of dark forces, from fixed target accelerator searches to precision astrophysical surveys, has returned only exclusion limits. There is no physical law that requires 27% of the universe to be one inert particle when our small corner of it is this complicated. We may not be missing a particle. We may be missing an entire second universe of physics running in parallel with our own. Invisible not because it's simple, but because none of our instruments were built to speak its language. Or the particle isn't heavy and structured at all. It might be so light it stops behaving like a particle entirely. Number 4. Fuzzy dark matter. In 2000, Weiyang-Hu, Renan Barkana, and Andrei Gruzanov were working on a persistent problem in structure formation. Cold dark matter simulations kept over-predicting the number of small satellite galaxies orbiting the Milky Way compared to what telescopes actually observed. Standard cold dark matter treats the particle as effectively a classical point mass, heavy enough that its quantum wavelength is smaller than an atomic nucleus, irrelevant at any scale astronomers care about. Hu, Barkana, and Gruzinoff proposed something radical in Physical Review letters, an ultralight particle, with a mass around 10 to the power of negative 22 electron volts, so light that its quantum mechanical wavelength, its de Broglie wavelength, stretches to roughly the size of an entire dwarf galaxy. At that mass, dark matter stops behaving like a swarm of particles and starts behaving like a single, continuous quantum wave, one coherent object the size of a galaxy, exhibiting interference patterns and a wave-like pressure that naturally smooths out the small-scale structure problems plaguing standard cold dark matter. Critics pointed out the model requires the mass to sit in an extraordinarily narrow range to work, and current constraints from the Lyman alpha forest have already ruled out large sections of the original parameter space. What survives is a universe where entire galaxies could be floating not inside a cloud of particles, but inside a single object exhibiting quantum behavior on a scale that should be physically impossible. If that's correct, every galaxy in the sky is wrapped in the largest quantum object ever theorized, and we are living inside it. Every candidate on this list assumes dark matter is something. One argument says we may be looking for a ghost that was never there. Number 3. MOND and the radial acceleration relation. In 2016, Stacy McGaugh, Federico Lelli, and Jim Schaumbert weren't trying to disprove dark matter. They were compiling rotation curve data from over 150 galaxies to test how tightly acceleration in a galaxy correlates with its visible ordinary matter. Standard dark matter cosmology predicts this relationship should be messy. Every galaxy has a different semi-random halo shaped by its unique merger history, so the correlation between visible mass and rotational acceleration should scatter widely from galaxy to galaxy. McGaugh, Lelli, and Schaumbert published their result in Physical Review letters and found the opposite, an extraordinarily tight relationship, now called the radial acceleration relation, where a galaxy's rotation can be predicted almost precisely from its visible matter alone, with almost no scatter across galaxies of wildly different size, mass, and history. Standard dark matter models struggle to explain why an invisible, randomly distributed halo would produce such a clean, deterministic relationship. That level of precision looks more like a fundamental law than a statistical coincidence produced by different halos. Proponents of modified Newtonian dynamics, MOND, first proposed by Mordechai Milgrom in 1983, argue this is exactly what you'd expect if gravity itself simply behaves differently at extremely low accelerations, with no dark matter required at all. Dark matter cosmologists counter that MOND cannot explain galaxy cluster dynamics or the cosmic microwave background without additional invisible mass anyway. Neither side has produced a knockout blow. The strongest argument against dark matter's existence comes not from a fringe theory, but from a straightforward, well-cited 2016 measurement that the mainstream model still hasn't fully absorbed. And then, 10 years earlier, came the image that made dark matter almost impossible to argue away entirely. Number 2. The bullet cluster. In 2006, Douglas Clow and his team weren't testing MOND directly. They were studying a spectacular cosmic collision, two galaxy clusters that had slammed through each other roughly 150 million years earlier. Observed with both the Chandra X-ray Observatory and gravitational lensing maps. Standard physics predicts that in any galaxy cluster, most of the mass sits in the hot X-ray glowing intercluster gas, and gravity should trace that gas closely. When the two clusters collided, the hot gas from each side crashed together, slowed by friction, and piled up in the center, exactly as expected. But when Clow's team mapped the gravitational lensing, the actual location of the mass, using the way background light bent around it, that mass wasn't in the gas at all. It had passed straight through the collision, separated cleanly from the visible matter, continuing onward as if nothing had blocked it. Physicists proposed instrumental lensing errors, unusual cluster geometry, or exotic modified gravity effects that could mimic the separation. None reproduced the clean, spatial split between visible mass and gravitational mass observed directly in the data. This is widely cited as the most direct empirical evidence that dark matter is a real physical substance and not simply a flaw in our theory of gravity. A snapshot of matter and gravity torn apart in the middle of a 150-million-year-old collision, still visible today. If dark matter is a fiction, it is a fiction that physically outran a cluster collision without being touched by it. So which is it? A particle we haven't caught, or a name for a mistake we haven't found? The final entry doesn't answer that question. It admits we never earned the right to assume the answer in the first place. Number 1. We named it before we found it. In the 1930s, Fritz Zwicky was measuring the velocities of galaxies inside the Coma cluster, a routine exercise in applying Newtonian gravity to cluster dynamics. Standard gravity predicted the galaxies should be moving slowly enough to remain bound to each other by their visible mass alone. Zwicky found they were moving roughly 10 times too fast. The cluster should have flown apart long ago unless it contained far more mass than could be seen. He called the missing component Dunkelmaterie, dark matter, in 1933, decades before any instrument existed that could test the claim. In the 1970s, Vera Rubin and Kent Ford measured rotation curves across dozens of spiral galaxies and found the same discrepancy on a smaller, more precise scale. Stars at the edges of galaxies moving far too fast to stay gravitationally bound. Every explanation proposed since has fallen into one of two camps. Either there is unseen matter, or our 200-year-old law of gravity breaks down at galactic scales. Neither camp has produced a final, undisputed answer. Dark matter was never the name of a discovery. It was the name of a discrepancy, a gap between what we see and what our equations demand, and for 90 years an entire field has organized its research, its careers, and its billion-dollar detectors around the assumption that the gap must be filled with something real. What if the only thing we've actually found, after 90 years, is the exact size and shape of our own mistake? Every entry on this list sits not at the fringe of physics, but at the center of its most trusted theories, gravity, particle physics, cosmology itself, all quietly disagreeing with the data at the largest scales we can measure. The universe isn't confused. It has been running on the same rules since before there were galaxies to obey them. We are the ones who built a name for the gap between our equations and our observations, then spent 90 years trying to prove the name was real. Maybe it is. Maybe 27% of everything that exists is a particle we simply haven't built the right machine to catch. Or maybe the universe has been trying to tell us for 90 years that the mistake was never in the sky. It was in the law we wrote to explain it. If you want to see more videos like this, click the video on screen now.